Hi, thank you all for coming. I'm Vince Buckland, and I'm going to present some work I've done in collaboration with Steve Mount and Graham Coop, looking at shared ancestry on the X chromosome. So just to review quickly why recent ancestry models are important in evolution. They pop up in many different areas. For example, detecting cryptic relatedness in GWAS panels is an important quality control step. Additionally, you can look at shared chromosomal segments of individuals in natural populations and identify where these come from to identify recent migration events. Peter, Ralph, and Graham Coop have done some really excellent work looking at demography and geography by looking at the length and number of shared segments in European populations. Also, there's been some really lovely work in anthropology estimating kin structure and family groups using ancient DNA and burial grounds, like Baca et al. 2012. And then my colleague Nancy Chen has done some really lovely work on building pedigrees in these Florida scrub jay systems, which can give us a lot of information about the ecology and evolution of these birds. So Graham and Steve and I were really interested in how we could extend these recent ancestry models to X chromosome data. And so far, most of these models just use autosome data, but as we found, there's lots of interesting things that we can learn about X chromosomes due to their interesting inheritance pattern. So this is a quick example to build some sort of intuition here. This is my Grammy, and we've done 23andMe, both of us. She's my paternal grandmother, as evident by this. The squares represent males, this is me, this is her, and the circles represent females. And because I share genetic material with her, if I were to look at the 23andMe data, we have these segments that are shared identically by descent, meaning that I've inherited these exact same chromosome regions from her directly. And we can look at the empirical distributions that we observe in the data and come up with summary statistics like the number of segments shared and the length of these segments shared, and learn something about recent ancestry. Inverting this, we may ask the question, if I have two individuals, Susan and Barbara, and I'm able to computationally infer that we share segments, what can we learn about our relationship in the past based on these empirical distributions? And this is just what 23andMe does. So my grandmother and I both have 23andMe, as I mentioned, and we share lots of segments. Fundamentally, recombination is limited over the generations back in time, so these segments are quite long. In some cases, there's actually chromosomes where we share no material at all. And 23andMe correctly predicts that she's my grandmother. It also predicts that my great-grandmother is my first cousin, which is wrong. So clearly there are some problems there. So what's interesting to note here is that we don't share any material on the X. And unlike these cases, like chromosome 9, 20, and 21, this isn't something that's a random chance. This isn't an unlucky coin flip. This is actually due to the inheritance pattern of the X chromosome. So here, just to refresh your memories, fathers do not pass an X chromosome to their sons. They pass a Y. And this actually gives us a great deal of information because it excludes all of these possible individuals if I inherit X material, if I share X material with another individual here. So that would mean that I must be sharing this material through my mother's side and not all of these ancestors. So Graham and I were really curious, if this excludes so many possibilities, how can we use this information? So first, I'm going to model an X genealogy back in time. Then I'm going to explain how the number of recombinational meioses varies across an X genealogy, which is kind of fascinating. And we're going to use a very simple model of recombination to learn about what these X segments say. So just to start, imagine that I have a present-day female named Barbara. And going back through the generations, K generations in the past, she has 2 to the K genealogical ancestors if we ignore pedigree collapse, which is what we do in our paper. So she has 2 parents, her mother and her father, both of which contribute an X to her. She has, on her mother's side, 2 parents that contribute an X to her mother. But then on her father's side, only her mother contributes an X, and her father is excluded from being in the X genealogy. So building this pattern back up through the generations, we can see that all of these blue nodes here are individuals that contribute, or can possibly contribute, an X genealogy to the present-day female. But all of these white nodes cannot. So they are excluded from this. So if we just want to ask the question, how do these X ancestors grow back through the generations, there's some really lovely mathematics that pops out if you like this kind of thing. If I look at this present-day individual, she has 2 X ancestors in the previous generation, 3 in the generation before that, or after that, 5 in the generation after that. And you'll see that the number of X ancestors in a given generation K is the sum of the number of ancestors in the previous generation and the generation before that. And if you remember your Fibonacci sequences, you'll know that this is indeed a Fibonacci sequence, such that the total number of X ancestors of a present-day female is Fibonacci k plus 2 back through time, ignoring pedigree collapse. So we can then ask the question, what fraction of our total ancestors are X ancestors? Now, both genealogical ancestors and X ancestors back through the generations increase exponentially, but X genealogical ancestors increase exponentially at a slower rate. So one's total number of X ancestors is a proportion of total, one's number of X genealogical ancestors is a proportion of total ancestors is decreasing through the generations, as evident in this plot. So there's something else interesting that happens here, and that's that if we ignore these regions on the X chromosome that undergo recombination in males, which are known as the pseudoautosomal regions, if we ignore those regions, recombination only occurs in females. So in this present-day individual here, she inherits this blue chromosome from her father directly without any recombination, and then recombination can possibly occur in her mother here. So what this means is back through the generations, if we ignore the pseudoautosomal region, there's no recombination in males in the X genealogy. So this means that across an X genealogy back in time, the number of recombinational meioses can vary quite considerably. So for example, I have a present-day female here, and going back 5 generations, we see that the number of recombinational meioses can vary at the most from 5 occurring. And this corresponds to the lineage in which there's a female every generation, and thus there's the opportunity for recombination in each of these generations. On the other end of the spectrum, there's this lineage that has males and females alternating each generation. And this is the fewest number of possible females, because just for refresh your memories, no two males can be adjacent in an X genealogy, because males pass Y chromosomes, not X's. So this shows that the minimum number of recombinational meioses is the floor of k divided by 2. So looking at this pattern, we want to know, basically, to model this. And so imagine that I'm a present-day female, and I don't know how many recombinations separate me between an ancestor and the kth generation. We're uncertain about this, so thus we need some sort of model that can express the probability of there being 5 recombinational meioses versus 3 or 2. And so the way that we model this is we thought about it in a combinatoric sense. So we find that if you think about the males as these purple circles here, and the females as these red circles, because no two males can be adjacent, the number of lineages with, say, R recombinational meioses is the same as thinking about this as having R red balls and K minus R purple balls and arranging them in all possible ways such that no two purple balls are adjacent. And that's what gives you this R plus 1 choose K minus R here. And again, that's the number of recombinational meioses, the number of lineages with R recombinational meioses with an ancestor K generations back. And then the probability of having that number of recombinational meioses is just that number divided by the total number of X ancestors. So with this model, we can then look at the number of segments that an individual would share, a present-day individual would share with an ancestor K generations back. I'm going to build this up in steps here. So here is an X genealogy. As I said, we're uncertain about which particular ancestor we're inheriting these X segments from. So they could be 5 recombinational meioses apart or 2 recombinational meioses apart. So we simply marginalize over all the unknown number of recombinational meioses here. We then have a Poisson model for the number of recombinational breakpoints that occur across these R recombinational meioses. And we can imagine this as, from me being a present-day individual to an X ancestor K generations back, there being a Poisson number, a random number of breakpoints on a single X chromosome, creating, and let's say that there are B of these random breakpoints, and that would create B plus 1 segments. Now, we simplify the true recombination process by ignoring sort of long-run dependencies, and we pretend that each one of these segments has an independent chance of surviving through these R recombinational meioses. So thus, the chance that N survive through all of these recombinational meioses is a binomial distribution here with probability 1/2 R, and here are the B plus 1 segments. And what this gives us is the probability that if I were to actually have an X ancestor, not my paternal grandmother, and we were to do 23andMe and we see that there are 3 segments, what's the probability of that? Is that likely? Is it rare? Etc. But what's fascinating about this is that we can invert this probability, and we can learn something that's not accessible through autosome data alone. So using Bayes' theorem, we can ask the question, if I have this distribution I previously derived here, what's the probability, the posterior probability of having R recombinational meioses, or in other words, R females in an X genealogy? So I'm ignoring some of the math here. In the previous section, I derived these results for a present-day individual to a shared ancestor in the kth generation. Here, and there's a lot more math I'm skipping over, but this is essentially the case of a half-cousin connecting to, a shared ancestor K generations back connecting a half-cousin. And so what I want to ask here is, what's the posterior probability of the number of females, basically, between this half-cousin and this half-cousin with this ancestor in the king's generation? So as an example of what this can give us, suppose that I observe that we have 3 shared X segments, and then using the autosome data, which is there's a larger total genetic map length, there's more signal there, we know a priori that this ancestor is 4 generations in the past. I can then, using this result, figure out the maximum a posteriori estimate of the number of recombinational meioses here. And what we find using this is that that maximum a posteriori estimate is 4. And what's fascinating about this is while these are all the possible genealogical configurations that can connect to half-cousins with a shared ancestor k generations in the past, that this is the most likely. And it's important to note that this is already conditioning on the fact that we already share X segments. So the total number of combinations on autosomes alone is much, much larger than this. So just by seeing X segments, we know that it's 34 possible genealogies. And then using the number of, the posterior distribution of R, we can narrow it down to this. So to conclude, X segments shared between cousins immediately rules out sort of genealogical shared ancestors. We can use the fact that the number of recombinational meioses, ignoring the pseudoautosomal region, varies across an X genealogy to learn something about the posterior distribution of R, of recombinational meioses, and thus learn certain things that we can't see in the autosomes alone. Unfortunately, it's important to note that the X is short. It's about 2 Morgans long. So this signal decays relatively quickly. But this may not be a problem because population genomic data sets are growing in sample size. And this is going to increase the number of pairwise relationships we see as we sample more deeply into populations. And these individuals share more recent ancestors. And also, our ability to detect identical by percent segments is also going to be increasing in these large segments. With that, I'd like to thank these people. Thank you. And I'll be happy to take questions. Yeah.
So this hinges on there being no recombination of males in the X chromosome. There are lots of species like Drosophila with no recombination of males. Do you apply this to that whole genome?
We haven't thought about that. For the most part, I mean, this is probably bad, but we're thinking mostly human here. Yeah. Are there any other questions? Yeah.
Practice, how are you defining segments?
That's a good question. So there's tons of, like, Beagle has methods to identify identical by descent segments. And we, for the most part, just treat those as like, that problem done. They're very strong methods, they're very robust. Any other questions? All right, thank you.